Okay, this is lesson 2 of module 5, functions. In the last lesson, lesson 1, we talked about the concept of a function and the fact that um, it can predict things. So in the example that we used, we could predict where a stone was going to be at a particular time in its fall, as it falls from some distance. And so we talked about the fact that we would want to maybe know for every time or time interval where that stone is. So we looked at a table and we saw that we needed more than the table. So in this lesson, we're going to formally define functions as rules that give us that predicting ability. And we're going to see that over the next few lessons, we're going to see that functions can be defined by an equation or a formula, but they might simply be a graph or a picture or a verbal description or a table of values. So we're going to look at those aspects of functions. Okay, so let's continue with our example. So here's our table again from the example in lesson 1 of the falling stone. And on the left is that table, and on the right is a slightly different table. So both of these give the number of seconds that the stone has been falling and its distance traveled. And over here, once again, some different time values and then the distance that the stone has traveled. So the directions here say make a conjecture about the differences between the two tables. What do you notice about the differences? They look very similar, but there's some important differences. So go ahead and pause the video, look at that, and then come back and we'll talk about it a little. Okay, so hopefully you've had a chance to look at the numbers here and kind of come up with some things. And one of the things you might have noticed is that in this table, as I go down here, I could, look, say, at 1 second and see that the stone has traveled 16 feet. But if I come over to this table, I could see for 1 second the stone has traveled 4 feet. And then also again at 1 second, the stone has traveled 36 feet. And then down here for 3, I've got, for the value of 3 seconds, I've also got 2 different predictions for where that stone's going to be. So you might say that this table is not a good predictor for me. It doesn't tell me definitely for every time value a single prediction for where it's going to be, whereas this one does. So that's kind of part of the definition of a function here, and we'll talk about that in just a second. But this table here is not a good predictor. It is actually not a function, whereas the first table is. So let's look at it in a little bit different light here. Okay, so here's our table from the first screen there, written a little bit differently. Instead of X, I'm calling number of seconds, I'm going to call T right here. So, but that's, really the only difference. Otherwise, the values are all the same. Again, for 1 second, I have 16 feet, and I don't have another prediction for 1 second. So we've rewritten this, and we could think of this, we could call this function rule, we could call this function, we could assign it a name. We could call it D for distance. And it's going to predict the distance for any time between, for T, greater than or equal to 0, and less than or equal to 4. So anytime between 0 and 4 seconds, this function can tell me where that stone is. So another way to kind of say that is to say that our function d assigns a distance for every number of seconds between 0 and 4. So instead of the way we have it over here, we could say d assigns 4 to 0.5. It assigns 16 to 1, 36 to 1.5, and so on. So we can think of it as an assignment. It assigns a value, some value, to each input of time. So okay, enough said. Okay, so another way to think of these functions is something that we like to talk about as a function machine. Okay, so here's d, our function d, and our inputs are time. So I say, okay, I want to know where that stone is at 2 seconds. So I put the value 2 into my function machine, and out comes a value of 64. So I could say that my function rule assigns assigns 64 to t equals 2 seconds. Okay, and then if I put 2 in again, I expect to get 64 out if this is going to be a good predictor or a good function machine. If I put 3 in, I'm going to get something different out. I'm going to get 144 out. If I put 1 in, I should get 16 out. And if I put 1 in again, I should still get 16 out. So it's a good predictor because it's reliable. Okay, so once again, for the function that we're talking about here, the function d that we've defined, the inputs are always going to be the time. I get to pick the time, and the function tells me the distance traveled. So time is the input, distance traveled is the output. And those are vocabulary that you definitely want to learn. So we have input and we have output. Okay? And another thing to remember about this function is that it only works for t greater than or equal to 0 and less than or equal to 4. So t has to be between 0 and 4 for this function to make sense. So, and so this function is kind of special in that it could be represented by a formula. Not every function has that feature. And the formula for this function is distance. I'm going to write it up here. Distance traveled, for time t is equal to, and that all goes together. Distance traveled for time t is equal to 16 t squared. And since we're calling the distance traveled by the stone y, we could say that this function is y is equal to 16 t squared. Okay, so in exercise 6 of the last lesson, you might have seen this relationship, but maybe you didn't. But we did kind of talk about the fact that each of these values here for distance were multiples of 16. So this one is 16 times 1. This one is 16 times what? 4. This one is 16 times 9. And this one is 16 times 16. So, so maybe you can see the association now of 16 times the time squared. 16 times t squared. When t was 1, keep having to change colors here. When t was 1, then 1 squared is 1, and the value of the distance is 16 times 1. When t was 2, 2 squared is 4. 4 times 16 is 64 feet. And so on. 3 squared is 9. 4 squared is 16. So we get the values back out for this function. So this function is special in that we do have a formula for it. We don't have to just rely on this table of values for it. So this function we've already seen represented as a table. And now we have a formula, and prior to that, we had this picture that showed the distances that it dropped for a certain amount of time, and we also had a verbal description about the stone dropping. So lots of different ways to describe a function. Okay, so we have Newton and Galileo to thank for this relationship, for recognizing it, for actually making measurements and noticing this pattern. So if you discovered that pattern, you can give yourself a pat on the back. And if you didn't, if all you noticed that 16 was a factor, that's great too. So in this problem set of this lesson, you're going to be challenged to find patterns between data like this. And they're really kind of, if you approach them as puzzles, they're actually kind of fun. Okay, now find exercise 1 in your classwork, in your notes. And we're just going to work out exercise 1 together. If you want to use a calculator for this, you can. We'll do the first one together, and then I'll let you work on the rest of them. So we're letting y be the distance traveled in time t. And we're going to use the function y equals 16t squared to calculate the distance the stone dropped for the given time t. Okay, so, and then we want to, in part A, we want to make sure as we compare these that they're the same as the distances from lesson 1 in the table. Okay, and you can look back to the table in earlier in this lesson, or you have it in your notes. Okay, so what we want to do is evaluate this function. So y is equal to t squared. And so if I want to evaluate for 0.5 seconds, I want to evaluate this function, 16 times 0.5 squared. Now you can punch that into your calculator, and that's fine, but I'm going to do it without doing that. So y is equal to 16. Now instead of 0.5 squared as a decimal, I'm going to go ahead and write that as a fraction. That's 1/2 squared. So this becomes y is equal to 16 times 1/2 times 1/2. So that would be 1/4. So y is equal to 16 times 1/4, or 1/4 of 16, which is 4. So y is equal to 4 when t is equal to 1/2. So go ahead, and this next one's easy, right? 1 squared is 1. 16 times 1 is 16. Okay, so go ahead and check those in this function, y is equal to 16t squared, and match it up to the table from lesson 1. So work on that and then come back and we'll continue. Okay, so the values you should have gotten by putting each of those values for t into 16t squared are shown here, and they do match. They do match the distances from that table in lesson 1. I've done one more calculation here on the screen. So I put in 1.5, which is 1.5 or 3/2. So 16 times 3/2 squared. 3/2 squared, which I have to do by order of operations first, right, is 9/4. 3 times 3 over 2 times 2. I can take a factor of 4 out of both of these, and I'm left with 4 times 9 is 36. So the value, the distance traveled in 1.5 seconds, was predicted to be 36 feet by this function, and that matches what we had observed measuring the stone actually falling. So it's a good predictor. This function here, this formula representation of the function, is a valid predictor of the distance the stone dropped for any time t. So that's the answer to part B. Does the function y equals 16t squared accurately represent the distance the stone fell after a given time t? In other words, does the function assign to t the correct distance? So we've already said, yeah, it does. It assigns the right values, 100 to 2.5, 144 to 3, and so on. It assigns the correct values, so it accurately represents the distance the stone fell. Okay, so we're going to, I'm going to state for you the actual definition of a function. And so a function is a rule that assigns to each input exactly one output. So again, we said that if it's going to be a good predictor, then every time I put in a particular input, and in this case that's a time, a value of time, I'm going to get exactly one output out. I'm going to get the same thing each time I do that. Okay, so some functions, but not all, can be described by a formula. And the function that we're working with right now can be described by a formula, thanks to Isaac Newton. But some functions can be represented by tables, graphs, or verbal descriptions, and other things as well. Okay, so if we think about our function that we had, y is equal to 16t squared, the formula that represents our function, we could put a different value in. We could put in t equals -1, and if we did that, we would get -1 squared is just +1, so we would get a distance of 16. But we think about, well, what would that mean? What would t equal -1 mean? Well, it'd mean 1 second before the stone was dropped. And so that's why we talked about the fact that our function is only well defined for between 0 and 4 seconds. It doesn't work outside of that. So it doesn't make sense to do this calculation here. Another calculation that wouldn't make sense would be this. What happens at t equals 5 seconds? We can get a value for that. 16 times 5 squared, or 16 times 25, which would be 400 feet. But this also isn't going to make sense because our stone is being dropped from a height of 256 feet, and that's as far as it can fall. So it can't fall 400 feet. So functions are only good usually within some certain range of values for the input. And we want a function that every time I put in one of these values, say t equals 2, I want to know that I can get exactly one value for the output. Okay, so let's look at some examples of that. So look at exercise 2 and 3. It says, can the table shown below represent values of a function? And so remember, if we're thinking of our definition of a function, that is a rule that assigns to each input exactly one output. So that's what we're looking for. And so for each input, I want to look at each input separately and see that it has exactly one output. So to do that, I can just look across the inputs and notice that none of them are repeated. So therefore, I've got exactly one output for each input. So this one, the answer would be yes. There's exactly one output for each input. Okay, so then if we look at number 3, we're going to do the same thing. We're looking that for each input value, there's exactly one output. But we notice in this table that we've got an input of 7 and an output of 15 here. And we've also got an input of 7 and an output of 10. So this one is no, it's not a function. Because I could say an input of 7 has 2 outputs. Okay, so it's not a good predictor. I can't know what the output for 7 is because there's more than one option for it. All right, so look at the next exercise 4. And what we have here is we're asked if this table could represent a function. So we look across the inputs and we notice that none of the inputs are repeated. So each input has only one output. So we could say, yes, this is a function. Each input has exactly one output. Exactly one output. Okay, hopefully you're noticing this element right here, that if I put in 10, I get out 32, and if I put in 20, I also get out 32. So, but that doesn't break the definition of a function, which says that each input has exactly one output. All the outputs could be the same, but still each input has its own output. And so every time I put 20 in, I know I'm going to get 32 out. Every time I put 50 in, 156. Every time 10 goes in, 32 comes out. So each input has exactly one output. So that might seem kind of arbitrary. You're saying, well, you can't, repeat inputs, but you can repeat outputs. So I'm going to show you an example, and it's actually the exit ticket from our last lesson, from lesson 1. I'm going to show you how it can make sense to have an output repeated. So if you remember this is a ball bouncing, and at 0 seconds it hits the ground, and we have data for every quarter second up through 1 second when it hits the ground again. So what I've done here is recorded a table of values. So I'm going to call this function h for height. So if I put in different values for t between 0 and 1 second, I've got 0, quarter second, half a second, 3/4 of a second, and 1. These are the outputs. So at 1/4 of a second, the ball is at 3 feet. At half a second, the ball is at 4 feet. At 0.75 seconds, the ball is at 3 feet again. So here's the same output for different inputs, but you can see why this makes sense because the ball's coming back down. And then here we have an output repeated again. At 1 second, the ball hits the ground again, so the height is 0. So here we have outputs repeated, but every input has exactly one output. I'm not trying to say that the ball could be 2 different places at 0.25 seconds. Okay, so hopefully that helps to give meaning to why that's our definition of a function and why this function is still a good predictor of where the ball is going to be. Okay, let's look at exercise 5 and then we'll be almost done. All right, exercise 5 says, it takes Josephine 34 minutes to complete her homework assignment of 10 problems. If we assume that she works at a constant rate, we can describe the situation using a function. Okay, so here we're going to go ahead and assume a constant rate of work. As you know from doing homework, it probably isn't a constant rate. Not every problem takes the same amount of time. But on average, we, in this situation, we're going to say that we can assume a constant rate. Okay, so predict how many problems Josephine can complete in 25 minutes. Okay, so pause the video and think about that. I'm not asking you to solve it. Just make a guess, make an estimate of how many she would complete in 25 minutes. All right, so a reasonable estimate for that would have to be something less than 10 problems because she takes 34 minutes to do 10, so she's not going to get 10 done in 25 minutes. So that somewhere in that ballpark would be a reasonable prediction. Okay, let's look at part B. So now we're being asked, we're told that this could be represented with a linear equation. So now we're going to go ahead and write a linear equation in 2 variables that represents her constant rate of work. Okay, and so we know that she could do 10 problems in 34 minutes. You know, so we could say that is her constant rate here. So I'm going to bump down to part C here and use the variables that are given here. The time taken to complete problems is going to be X, and the number of problems completed is going to be Y. So I know that she can do Y problems in X minutes, and that is also equal to our constant rate. All right, so this looks like one of those distance time problems here. So I'm going to get rid of that. Those are both equal to the same constant because we're assuming constant speed for her homework assignments. And so I can write that equation there. And so I'm going to do the same thing that we've done. I multiply both sides by x. I'm going to get this equation in the form that I want it. So it's going to look like this. Let's write it over here. Y is equal to 10 over 34 times x. Okay, because I had the x's cancel here, so I'm left with just y is equal to x times this ratio here. Okay, so I'm going to use this equation that we wrote in part B, which is right here. There's our equation, as the formula for the function to complete the table below. Round your answers to the hundredths place. So you're going to want to use a calculator with this and go ahead and put in the different values for x that are represented here. So this is going to be 5 minutes. So in 5 minutes, she could complete 1.47 problems. So that would be putting in 5 for x and multiplying by 10/34. We could simplify that 10/34 and write this equation as y is equal to, dividing out a 2 on both of those, 5/17 times x. So that makes it a little simpler, but it's the same function. It's the same linear equation. Okay, go ahead and pause it, get a calculator, round to the hundredths place. So this is 7 in the hundredths place, so round each of these other values off. Okay, so we'll look at each of these. If x is 10, then I've got y is equal to 5/17 times 10. So y is equal to 50/17. And that number, written as a decimal, is 2.94. So in 10 minutes, she can do just under 3 problems. Okay, so each of the other values, I'm going to get 4.41, 5.88, and 7.35. Okay, so in 25 minutes, that's the one we made a guess at, she would complete about 7 1/3 problems. So if you guessed somewhere in the vicinity of 6, 7, 8, you were pretty close. So part D asks you to compare your prediction from part A to the number you found in the table above. So whatever you got for it, you can write a comparison there. Okay, now let's look at part E. It says use the formula from part B to compute the number of problems completed when x equals -7. So our formula was y is equal to 5/17 times x. So if x is -7, I would have y is equal to 5/17 times -7, and that would be y, using a calculator, I'd get y equals -2.06. And then we're asked, does your answer make sense? And explain. So the answer doesn't make sense, right? Well, hopefully you've thought about this. If you haven't, you might want to pause the video. But the answer doesn't make sense because the input doesn't make sense. It doesn't make sense to put in -7 minutes of working on your homework. Although, well, anyway, I won't say that. So it doesn't make sense the input doesn't make sense, and a negative output, getting -2 problems done, doesn't have any meaning in the context of the function that we wrote. Okay, so so anyway, a negative output doesn't make sense and a negative input doesn't make sense here. Okay, part F. For this problem, we assumed that Josephine worked at a constant rate. Do you think that is a reasonable assumption for this situation? So you could write whatever you think here. Probably most of you have the experience that homework does not happen at a constant rate. Sometimes you can zip through 3 or 4 problems and then spend all your time on the last one or something like that. So probably not that reasonable. But of course it would depend on the type of problem that you're doing. Okay, so let's look at kind of a summary of this. So you have this on your problem set page, and it restates what we talked about. A function is a rule that assigns to each input exactly one output. So if I put a value for the input in, I will be able to rely on this rule or table or whatever it is to give me an output, exactly one output. It's not gonna change it up on me. And by doing that, the phrase exactly one output must be part of the definition so that the function can serve its purpose of being predictive. We want it to be a valid predictor and a consistent predictor, that it's not flip-flopping on me. So functions are sometimes called input-output machines, or can be described as an input-output machine. So if we have a function d, the input is time, the output is distance traveled in however many seconds, whatever seconds we have there. So, okay, so we have looked at a formal definition of a function. And like I said, in this problem set, you are going to be asked to identify functions in tables. We did some exercises like that. But you're also going to be asked to find some function rules too. So have fun with that. And we'll see you back here for lesson 3.